All right, so we were studying volumes of revolution, and one thing that's really important to think about when you're doing a solid of revolution is making sure you know what is it rotating around. And this particular question asked us to rotate um, y equals arc sine of x. So this cute little thing, and the lines x equals 1 and y equals 0. So x equals 1 is just a vertical line. Y equals 0 is just the x-axis. So that little triangular-ish thing. And I'm very grateful that the question asks us to rotate it around the y-axis. If it asked us to rotate it around the x-axis, it would be a lot more challenging. Off the top of my head, I'm not sure if I would be able to do that. So if I wanted to rotate it around x, then I would set up that the volume of that solid, so that would be rotating, so it kind of carves out this sort of a shape here. If it wanted me to rotate that around x, then the volume would be the integral from 0 to 1 of pi, and each of those is a circular disk, and the circle has a radius of arc sine of x squared, and each disk has a width of dx. So the tricky thing is I'm not sure that I am able to do that integral. I would try integration by parts and then hope and pray that it works out. It may work out. The question that is in the textbook actually rotates around the y-axis though. So if I want to rotate it around the y, what I need to do is invert my equation. So my equation, instead of being y equals arc sine of x, my equation becomes sine of y equals x. You can see that the black line, the black curve, goes right on top of the blue curve there, but it's restricted to only being along the domain um, from where x is negative 1 to y is to x is it's restricted along the range from where y is equal to negative pi over 2 up to positive pi over 2. And so you can actually program that in here using the squiggle brackets. Negative pi over 2 is less than or equal to y, less than or equal to positive pi over 2. And so now they have exact overlap. So if I want to find the volume rotated around the y-axis, I need to figure out what those y values are. And those y values are negative pi, or not negative pi over 2, excuse me, because I wanted to do, my old one was from x equals 0. So it's y equals 0, because if x equals 0, you do arc sine of 0, which is also 0. And then up to 1, if you do x equals 1, you get y equals pi over 2. So from 0 to pi over 2 of pi times sine of y squared dy. And so now I'm not creating this shape that was down there in red. I'm rotating it around the y-axis. So it's making this kind of, I don't know, nice looking shape here. Okay, so to do this integral here, we have to remember something about sine of y. So I'm going to go over on the side, and I remember that the cosine of 2 theta, and this is in your formula packet, but it's very useful when you're dealing with trig integrals to keep this in mind, that cosine of 2 theta is equal to um, cosine squared theta minus sine squared theta. That's usually the form that I have memorized. In this particular problem, I care about sine squared, so I'm going to rewrite cosine as 1 minus sine squared. So I can now say that cosine of 2 theta is 1 minus sine squared theta. If I add sine squared theta to both sides and then subtract cosine of 2 theta, oops, there's 2 sine thetas in this line here. There's 1, 2, so 2 sine thetas. So if I add 2 sine theta to both sides and subtract cosine of 2 theta, I get this. So I know that sine squared of theta can be replaced with 1 minus cosine of 2 theta over 2. So now my integral becomes same bounds from 0 to pi over 2, 1 minus cosine of 2 theta over 2 d theta. We can just pull the 1/2 in front. The antiderivative of 1 is just theta. The antiderivative... Oh, I'm sorry. I switched to theta, and I should have just kept it as the letter y. Because I didn't do a trig substitution. I just did a trig identity. And identity means it stayed exactly the same. So I don't need to switch my letters. I don't need to worry about what d theta is. I'm just going to use the letter y. So I have cosine of 2y. So the antiderivative of 1 is just y. The antiderivative of cosine is sine. But because it was cosine of 2y, I have to divide by 2 to counteract the chain rule. Because if you took a derivative, you would multiply by 2. So we're doing an antiderivative here. And that's going to get evaluated from 0 up to pi over 2. And so then my volume is whatever answer I get when I plug that in. So 1/2 times pi over 2. And if you plug in pi over 2 to sine of 2y, you get sine of pi. There we go. One more parentheses so that everything is getting attached to the 0. So we have 0 minus sine of 0 over 2. A lot of that is 0. Well, this is 0. Sine of 0 is 0. Sine of pi is also 0. So I guess we just get a super nice answer. Volume is pi over 4. So the really nice thing about this problem is sometimes as a student, you like things to be in terms of x. And so you're like, oh, integrating and rotating around the y-axis is harder. But conceptually, all you have to do is just write your bounds of integration in terms of y and write your function in terms of y instead. So I went from y equals arc sine of x to sine of y equals x, and then everything just kind of popped out a lot nicer. The other tricky thing is using this right here. This is a very useful tool to have down, that your double angle formula for cosine allows you to deal with sine squared integrals or cosine squared integrals. So please comment, ask questions if there's anything I can do, and let me know.